Hope you're all settled in. I personally really enjoy talks with the lights dimmed so low, because it means that I can have a nap if I want to. All right. Thank you all for coming. Good afternoon to all of you. Today we're going to be talking about statically typing JavaScript, or tackling the beast. So before we get started, a little bit about me. Just want to introduce myself. I'm a software engineer at MemSQL. We're a database startup, and we develop a high-performance, hybrid workload, distributed SQL database. Lots of buzzwords right there. And at work, I like building user interfaces, and at home, I like playing with mechanical keyboards and other things as well. The team that I work on at MemSQL specifically works on everything around our core product, the database. So we work on all the UIs and all the tooling, all the infrastructure on top of the database that is a main product that we sell to our customers. And we adopted some form of gradual typing back in 2014 with the typing module for Python 3. And we also adopted typing in JavaScript in February 2016 when we started using tcom.js, which is a very ancient typing library for JavaScript, way before TypeScript was popular. And today's talk is going to be three main components, although the last one is really just the most important one. The first one, we're just going to do a brief overview of static type systems and what they mean. Then we're going to go on and talk about the historical nature of statically typing JavaScript. And then we're going to be talking about Flow and TypeScript. And just before we get started, I wanted to do a quick question. Does anybody here use Flow or TypeScript or perhaps Google Closure Compiler on a weekly basis? All right, quite a few hands up. Very happy to see that because I have strong beliefs on this field. So just they're all on the same page. The main difference between statically typed environments and dynamically typed environments is that in statically typed languages or statically typed systems, the type of a variable is known at compile time. So the type of an expression or a variable is a static time concept and not a runtime type concept, which is the case of like Python and JavaScript. Whereas on the other hand, statically typed systems, we have Java, C++, and other languages. Note, though, that we're now starting to see gradual typing evolve. So things like TypeScript and Flow and Sorbet for Ruby and MyPy for Python, all of those sit somewhere in the middle between static typing and dynamic typing because expressions have a static type, but they also have a dynamic type. And it can be different from the static type. We'll talk more about that later. Before we go on, though, I wanted to just present my opinions as to why I think that static types are important, especially in JavaScript. But since most people here in the room already seem sold on the idea, because most of you are already using them, I don't want to spend too much time here. I just want to mention that static type systems help us avoid a myriad of runtime type errors and other sorts of bugs. They also allow us to spend less time writing tests. And they also allow you to diminish your bundle size, especially in JavaScript. And they enable amazing runtime type. They enable that you don't need to have runtime type checking, which also lowers your bundle size. And they enable amazing IDE features, such as mechanical refactoring, jump to definition, autocomplete, IntelliSense, all of those things that Java developers are so accustomed to. There's a few other advantages, and you might be wondering what the beast is from my first slide. Well, the beast is JavaScript. Because JavaScript is an incredibly flexible and dynamic language, you can do all sorts of crazy things like the one on this slide, which doesn't make any sense. Or you can do implicit or silent conversions between any types to pretty much any type you want. And I really like that first example there because that's an actual bug that we had a couple of years ago in our own code. And without static type systems, basically, you can do whatever you want with JavaScript. And that's a big problem for most medium to large size applications. And so since JavaScript is so dynamic and so flexible, adding a static type system on top of it is really hard because static type systems are normally strict. They normally force you to play by the rules, which JavaScript doesn't like. It doesn't like rules. And so I want to try and understand with you guys why it took 25 years for us to go from the invention of JavaScript back in 1995 to today, where most people in the room are actually using static type systems on top of JavaScript. And the first piece of research actually came out in 2005 by Peter Thiemann, where he first theorized the idea of a static type system on top of JavaScript. This very first academia paper was purely theory, pure type theory, pure maths, and the author tried to explain how a type system could, in theory once again, reduce the number of errors in your JavaScript code. 2005. 4 years later, the same author and two colleagues actually worked on a proper prototype, which I believe was the first static type checker for JavaScript called TAJS, which is actually still in development today. And in this paper, they actually published their findings of running their type checker prototype on top of example JavaScript programs, and they concluded that type checkers could immensely help JavaScript engineers because they caught a lot of errors at a compile time phase. Another interesting paper from 2011 is called Typing Local Control State Using Flow Analysis, which is the basis for both Flow and TypeScript, because it was this type of research around flow analysis that allowed us to have features in Flow and TypeScript, such as type refinement, which is when the static type checker actually understands your code. Because nowadays, most type checkers actually understand what your code is doing, and they understand that the types of expressions and variables are actually changing as you run ifs and elses. But all of that is only possible today thanks to research like this. Then we have the TypeScript introduction paper and the Flow introduction paper from 2015 and 2017 respectively that explain the design goals of both tools. And so from a high-level overview, we have this timeline where even to this day, we're still doing research on how we can make static type checkers for JavaScript safer and more efficient. But it took a long time for us to get here. Google introduced Google Closure Compiler in 2009, which was the first industrial level type checker for JavaScript. And then TypeScript came out in 2012 and Flow in 2014. But the first releases of these two tools were only a shadow of what they are now, because they've evolved a lot since then, and actually there's still a lot of work to be done on both of them. And now we'll go to the third and most important part of the talk. We'll compare Flow and TypeScript, the two most popular tools for statically typing your JavaScript code, and we'll understand how Flow and TypeScript are different. When do they think differently about your code? So, first of all, a brief recap. Flow is developed by Facebook, TypeScript is developed by Microsoft. They're both actively developed somewhat, and they have different focuses. So if you go on the Flow design goals document or the TypeScript design goals document, you'll find that Flow and TypeScript have different goals. Even though they're both type checkers for JavaScript, they have different design goals. Flow is focused on performance. In fact, Flow was built to type check the 12 million lines of code that JavaScript that Facebook had at the time on a single repository, whereas TypeScript was built for VS Code and for Xbox Music, which only have around 200,000 lines of code. And then Flow was also built with a focus on correctness, whereas TypeScript was built for adoption. The designers behind TypeScript were trying to create something that people would actually adopt and use every day. They both support Babel, and they're both used by large popular open source projects. So React, for instance, is built with Flow, and Angular is built with TypeScript, and most large-scale popular projects use one or the other because any large project really needs static typing. And so at MemSQL, where I work, we've actually used both. We used Flow for over a year, and then we've been using TypeScript for over 6 months. And so I'm in a good position to compare the two of them. So let's start by looking at the syntax. It's very similar. The way to declare types in both Flow and TypeScript is very similar. The only major difference is that object types in Flow require the pipe operator if you want them to be exact, whereas with TypeScript, object types are exact by default. But other than that, the syntax is very different. There's only a small few names that are different and small pieces of syntax that are slightly different, but overall, the actual structure of the language is similar. In TypeScript, you have to name your arguments of functions. So when we have action up there, you actually have to name the argument of the action function. Whereas with TypeScript, you can actually just have unnamed function types. But all in all, it's all very similar. Where do Flow and TypeScript actually differ? And that's in the type system. It's how they think. They think differently about your code. And before I explain to you why they think differently and how they think differently, I just want to explain what a sound type system is. Is anybody here familiar with the concept of a sound type system? All right, so a sound type system is one that basically catches all runtime type errors. It's a type system where all the static types of all expressions and all variables correspond to all the dynamic types that they can have at runtime. So normally, one would say that Java or C++ or C# have sound type systems, but that's not necessarily true. For instance, Java is not 100% sound. I believe only like Haskell and OCaml are actually truly sound, because it's really hard to have a type system that enforces all types to be correct at runtime. And so let's start with this simple exercise to understand what all this soundness thing really means. We have a function called getFirstSize. It takes in an array of numbers, and it returns the first element in the array. What should a type checker, what should Flow or TypeScript infer the output type of this function to be? Remember, we can pass a number, or we can pass an empty array, which will have the function return undefined. So who can tell me what the return type of the function should be? Maybe number. So number or undefined. Any other suggestions of what the return type could be? Well, some would argue that it could be just number. And in fact, that's what both TypeScript and Flow choose. When you try to index an array with a number of type t, and array is just a generic type over some type t, both Flow and TypeScript choose just t. So basically, both Flow and TypeScript ignore the fact that when you try to grab an element from the array, it may not actually be there. So they both choose something that's incorrect. It's obviously incorrect, but they both choose it, and Google Closure Compiler shows the same thing, because it's more convenient. You don't want the type checker to tell you that when you grab an element from the array, it may not be there. That would be incredibly frustrating to actually write code against, and it would force us to have too much runtime code. So adopting any tool that made the other assumption here would actually be very annoying. Now I have another example. I have a type engineer with only one field, experience of type number, and I try to declare a variable of type engineer, but I put too many properties in. TypeScript obviously errors. Makes sense, right? But what about here? We have a function that takes in an object with 2 arguments, and this is actually from our own source code. It takes in an object with 2 properties, a database name and a table name, both of which are type string. And you pass to it an object with more properties, but it doesn't complain. And the reason it doesn't complain is because of width subtyping, because TypeScript basically chooses the most convenient option. It doesn't make sense for it to error here, because there's no world in which there could be a runtime type error caused by this. And so basically, TypeScript accepts that you pass a wrong type to that function, because it only cares about there being at least the properties that the function expects. This is called width subtyping, and it's actually very useful. And Flow also has it. So it's technically unsound, because on the return line up there, obj, the variable object, could actually have a value that doesn't correspond to its static type. Now I have another example. We have a type engineer, name, string, age, number, and we have a function called promote engineer that takes in an engineer and doesn't return anything. And then we have a type whale with the same structure, name, string, age, number, and we declare a variable of type whale called myWhale, and then we pass the whale to a function that expects an engineer. If you come from a Java background, this may be super weird, because Java doesn't accept this, and neither does C++ or C#, because they are nominally typed languages. However, both Flow and TypeScript are structurally typed languages, which means that they only care about the structure of the objects that you pass to a function and not actually what their type names is. And this just happens to be the most convenient thing for JavaScript engineers. We like writing functions that care about the structure of the arguments and not the actual names of the types. And so, once again, Flow and TypeScript made a purposeful choice on their design system to actually fit the minds of JavaScript engineers. And now I have my favorite example of all, and this one might be tricky. So we have a function f, and it takes in an array of strings or numbers. And note that this is not an array of just strings or an array of just numbers. The way the notation works is that ARR could be an array of strings and numbers, all in the same array. And we declare an array of strings, and we try to pass it to the function. Does everybody think this is valid? Does this look like an OK program? Anybody disagree? OK. So yeah, I see what you see. It makes sense. I'm passing an array of strings to a function that expects an array of strings or numbers. But what if I do this inside the function? If I mutate the array, note that a type checker cannot understand that mutation because it could be inside an if-else block. It could depend on user input. And so it's really hard for a type checker to understand that annotation. And then when I try and grab the third element from the array and I call 2 lowercase on it, what do I get? I get a runtime type error because s, the variable s, even though TypeScript thinks that it is a string, in this case, it is actually a number. And so that program is incorrect because it would error on that line. Flow actually doesn't let you do this because Flow's type system doesn't allow you to pass an array of strings to a function that expects an array of strings or numbers, which is very neat. But TypeScript is OK with that. So we can say that TypeScript made the convenient choice. TypeScript chose to accept something that is convenient for JavaScript engineers, whereas Flow is more strict. Flow actually rejects this program because it is not 100% safe. Flow with error on that line, even if your function f is empty. OK. Any questions about those examples, or should we leave questions for the end? Oh, actually, we have 2 minutes in the end for questions, so I'll leave it to the end. Let's talk about type inference. Let's see how TypeScript and Flow differ on type inference. So everybody knows in JavaScript, if you add an empty array to a number, you get a string. That makes perfect sense. Both TypeScript and Flow disallow this. They will both error on this, even though it's OK in JavaScript. So both of them made the conscious choice to not support this JavaScript pattern because it doesn't make sense. But what if we try to create a function that takes one argument and returns that same argument added to itself? And then we try to call that function with an incorrect argument, such as another function, because you can't add functions to themselves. Flow will error when you call the function, because it will say that this is not a valid argument. Flow knows that the only valid arguments for this function are either strings or numbers. However, TypeScript errors when you declare the function, and it asks you for a type annotation. TypeScript cannot infer that the type of n is number or string. It asks for a type annotation. And this is a big difference between Flow and TypeScript. TypeScript needs a little bit more help. And if you didn't fully understand that, let's look at another example that highlights pretty much the same thing. We have a type connection, which is an object type with only one property, ID, number. And we have a function called getConnection that's implemented somewhere else that returns a connection. And so we call getConnection to get back a connection. Later down below, we implement a function called resolveConnection that returns a promise that always resolves connection. And if you try to call this function, oh, by the way, the type of this function is promise over connection. Makes sense. And if you try to call that function in Flow, no errors, it understands that con right there is of type connection, and it doesn't complain, everything is fine. But TypeScript errors right there, because it doesn't know what's the type of con. It cannot understand that con is a connection, even though it will always be a connection. And so you have to manually annotate the function in order for TypeScript to understand it. This is just another example of TypeScript's type inference being inferior to Flow's. And I have another example, which I really like because it's a classic one that happens to everybody who tries out TypeScript. We have a type player, name string, age number, and the position is a discriminated union of the strings striker and goalkeeper. And then we declare a function of type, we declare a type f that corresponds to a function that takes no arguments and returns an array of players. And we try to implement our variable f1 of type f. And so we try to implement a variable f1 that is just a function that returns no arguments, that takes no arguments and returns an array of players. And Flow accepts this program, no errors, because it knows that array ARR is a valid array of players. And so it accepts this program. But TypeScript does not. TypeScript doesn't understand that ARR is a valid array of players because it doesn't understand that all of the positions in that array are valid positions according to the player type. And so you have to manually annotate the variable in order for TypeScript to accept your program. And just once again, we have another example of where TypeScript's type inference falls short. So if you look back at all the examples that I've just showed you, you can truly understand that both Flow and TypeScript are living up to their goals. TypeScript is a little bit more convenient because as per their design goal, they're not trying to build a sound type system. They're trying to build a static type system that strikes a good balance between program correctness and developer productivity. They're worried about developer adoption. But Flow, they are trying to build a full sound type system. And so it is a little bit more strict. Also, we can see the Flow's type inference is more powerful than TypeScript. So your TypeScript code will end up being much more noisy because you're going to have to annotate pretty much everything. Whereas with Flow, you can leave annotations out and your code looks more like normal JavaScript. And so, as I said at the start of the talk, we actually migrated 30 to 40,000 lines of code from Flow to TypeScript around 6 months ago. And the reason that we did that is because even though Flow's type inference is more powerful, and even though Flow catches more errors, there's other things that are more important to us, such as a vibrant community, help when we need it online, and good interaction between the developers of the tools that we use and the community that uses those tools. And so, because Flow is developed more internally at Facebook, they don't have the sort of interaction with the community that I want from a tool that I have to use every day for all of our code. And that's okay. I'm grateful that Flow is open source, but they just don't have the resources right now to work with the community. Besides, there were a few other issues with Flow, like using too much RAM and other small things that annoyed us a little bit. And so we moved to TypeScript, and we also hit some issues with TypeScript along the way, such as its performance being slower than Flow's, and also not having a few features that we wanted from Flow, as well as the type inference being much more inferior. So I'm actually hopeful about TypeScript because the community is growing really, really fast. I think it's the fastest growing language on GitHub right now. And all the features that I want from TypeScript, such as variadic types, are in the roadmap, and I believe they'll be implemented sometime soon. So what are the takeaways that I want people to have from this talk? The most important one is that there is no single solution for adding a static type system on top of a dynamically typed language. There's a triangle. There's a triangle of type check performance, which we can also say complexity, friction, and soundness. You can't have a fully sound, simple type system that can be easily adopted by everyone. You have to pick two sides of this triangle. And Flow and TypeScript shows different sides of this triangle. And it makes sense. And some proof of that, if you want, is this paper from some Microsoft researchers that forked TypeScript and made it more safe. So they made the type system of TypeScript more sound by catching more errors. And it made the performance of this system 15% slower because you can't have a fully sound type checker that is also insanely performant. And also remember, if TypeScript were safer, less people would adopt it because it would be harder to migrate JavaScript code bases to this new system. Secondly, I just want to say once again that After porting or migrating 30 to 40,000 lines of code from Flow to TypeScript, I really do think it was worth it. I have no regrets on my mind because there's a lot of benefits to TypeScript versus Flow. For instance, with TypeScript, you can choose how strict you want the type system to be. You can choose varying levels of strictness, if you will, and that allows each team to choose how strict they want their type system to be. Me, I prefer a more strict system, but I understand if other teams want a less strict system. That makes sense as well. And that's one of the main advantages of TypeScript, is the configurability. And finally, another important takeaway is that gradual typing is a thing that's real and that I believe more and more people will start adopting. 20 years ago, you had two options, JavaScript or C++. And what I mean by this is that you either used languages that were very, very strict, or you used languages that were very, very dynamic. There was no in between. Now, with gradual typing landing in Ruby 3, gradual typing landing in Python 3, TypeScript and Flow being more popular for JavaScript, people actually have a choice, which is gradual typing. You can have any's in your code if you want to, and you can have a varying level of strictness depending on how strict you want your project to be. And that to me is exciting because there is a market out there. The industry wants gradual typing because you shouldn't have to make a choice between something as flexible as JavaScript or as strict as Java. There should be an in-between. And so just before we end, I know this might not be the right audience, but it's worth a shot. We're trying to hire an experienced Go engineer for our team. And so if you're interested, just talk to me after the talk or email me at david@mypsycho.com. And thank you very much for your time. Let me know if you have any questions.
Hey, you were talking about all the configurations you can get with TypeScript compiler. Can you share what kind of configurations did you use for the examples?
All examples have no implicit any turned to true, and all the other strictness levels set to false. However, I made sure that the results would be the same if strict was true. So basically, you can just assume that all of them had strict set to true in TypeScript. The unsound example in TypeScript that I showed with the array would happen with strict set to true. There's no way TypeScript can catch that, even with the strictness at the highest level.
Hi. Can you say more about the performance difference between Flow and TypeScript?
Yeah.
About your experience?
Yeah, so basically, on our main repository that has 30,000 lines of code, rechecks, which are basically, a recheck is when you have your file watcher running and you save a file, and it runs type check on all of your project. Rechecks with Flow were never higher than 1 second. And with TypeScript, they can be around 5 seconds. This doesn't end up mattering that much because most of the time, you only care about the file that you're looking at. And so when you write some code in VS Code, for instance, the TypeScript information is completely real time, less than 100 milliseconds for the same file. The problem is when you want to know if you created any type errors across the entire project, and that can take a few seconds, which with Flow was never the case.
So we're discussing compile time performance, not runtime.
Runtime is the same.
It's always the same, right?
Runtime is the same because, in fact, when we switched, our runtime bundle pretty much didn't change because we're still using Babel with the same Babel configuration. So the runtime code is essentially the same.